So we were having a little look at where is it? We're having a little look at this test your understanding part, which was the C4 2014, and we're having a look at this question here, which is find dy by dx of this, and then find the values for dy by dx which are equal to 0. So let's have a look at this first of all. Let's write it out. I think most of you have already had a little go at this. So x squared plus y squared plus 10x plus 2y minus 4xy is equal to 10. Now, the first thing I'm going to try and look for is anything that's multiplied, which is that 4xy. So I'm going to do that over in the corner because that's the product, isn't it? So let's write u is equal to 4x. V is equal to y, because you've got those two things multiplied by each other. So du by dx is equal to 4, and dv by dx is equal to dy by dx. If I sub that into u dv by dx minus v du by dx, that's equal to u, which is 4x, times by dx, so 4x dy by dx plus, why have I put minus there, u dv by dx plus v du by dx, so v is equal to y, so it's going to be 4y. So this, just so we know, this part here is the differential of, oh, there's a minus in front of that, which is really annoying. It's the differential of this part here. Just be careful of that minus now. Okay, so let's go through and differentiate all of these then. So differentiate the 2x, differentiate x squared is going to be 2x. Differentiate y squared, you need to differentiate the 2 and then differentiate inside that and multiply by it. So plus 2y dy by dx plus 10x differentiated is just 10. Plus differentiate 2y, that's going to be 2 dy by dx. Differentiate this highlighted part, which I've already done on the right, which is going to be minus 4x dy by dx. Oops. Dy by dx minus, because it's minus minus, is minus 4y, and if I differentiate the 10, that's just equal to 0. If I want to find out what dy by dx is, I need to put everything with dy by dx on one side, everything else on the other side. So let's keep dy by dx on the left. So 2y dy by dx minus 4x dy by dx is equal to, let's take the minus 4 over first, so 4y minus 2x minus 10. Let's take the dy by dx out and then divide by it. So dy by dx is equal to 4y minus 2x minus 10 all over 2y minus 4y. So there's my dy by dx. That's part A.
Sir,
Yeah.
where's the 2 dy dx over dx?
So the things, I'm just going to go back a stage here because I've made a little mistake. So let's get rid of all of this actually. So the things which have got dy by dx in are, I should probably highlight them just so I make it really clear. 2y dy by dx, which is here. 2 dy by dx, which is here. And this one here which is minus 4x dy by dx. So let's keep all of that on the left-hand side. Let's take everything else over to the other side. So I end up with 2y dy by dx plus 2 dy by dx minus 4x dy by dx is equal to 4y minus 2y minus 10. Now I'm going to take dy by dx out and divide by all of that. Now I am actually going to do that this time because there's 3 terms just to show. So dy by dx taken out as a common factor, which leaves me with 2y plus 2 minus 4x is equal to 4y minus 2y minus 10. So then dy by dx is equal to 4y minus 2x minus 10 all over 2y plus 2 minus 4x. So there's dy by dx. Now the next part, B, says find the value of y, or the values of y, for which dy by dx is equal to 0. 5 marks. Okay, so here we want when dy by dx is equal to 0. That's what we want. So if I sub that into here, I end up with 0 is equal to 4y minus 2x minus 10 all over 2y plus 2 minus 4x. Now you might think to yourself, well, this is in terms of x and y. How can I find out values of y if it's in terms of x and y? Now, the thing is that we've also got another equation in terms of x and y, haven't we? Which is this one up here. So what we've got is we've got 2 equations in terms of x and y. To solve them, we need to solve them simultaneously. So the first thing I'm going to do is I'm just going to times by the bottom here, which will get rid of all of that because it's times by 0. So I end up with this, which is 0 is equal to 4y minus 2x minus 10. But the other equation I've got is x squared plus y squared plus 10x plus 2y minus 4xy is equal to 10. I'm going to solve these now simultaneously. So the first thing I'd probably do is I'd probably rearrange for x. Now the reason I'm going to do that on that top one is because, just give myself a little bit more room. So if I rearrange for x, so let me just write this one down. So if I'm writing 1 down, I've got 0 is equal to 4y minus 2x minus 10. If I divide this by 2, I end up with 0 is equal to 2y minus x minus 5. So if I take the x over, I end up with x is equal to 2y minus 5. There, like so. This is what I'm going to substitute in to this equation here now. So let's sub that in. I'm replacing the x. So that's going to be 2y minus 5 all squared for the first x squared plus y squared minus 10 times by 2y minus 5 plus 2y minus 4y times by 2y minus 5 is equal to 10. So let's square this first term. I end up with I end up with 4y squared minus 20y plus 25 plus y squared minus 20y plus 50, expanding that out, plus 2y, I put that equal to 0 instead of 10. Let me just check. So I think I've copied the equation down wrong, which is plus 10x, and I put minus 10x there. So I'm just going to change that. So that's plus 10x, and that is plus 10x, which means that this is going to be equal to plus 20y, and that this here is equal to minus 50. Yeah, like so. So 4y squared plus y is 5y squared. Take away y is 8y is equal to minus 3y squared. Let's highlight in the next one. Minus 20 plus 20, that's going to cancel. So 2y plus 20y is equal to plus 22y. Then 25 minus 50 is minus 25. So minus 25. Let's take everything over to the other side. So 0 is equal to 3y squared minus 22y plus 35. Type that into our calculator to find out what our answers are. So we've got 3y squared minus 22 plus 35 is equal to 7 over 3 for y. And y is equal to 5. So let's just check those answers. 7 over 3 and 5, yeah, we got there. Brilliant. Super. Tricky questions there again. Loads of working. But these are the questions which are going to come up. Everything you've done so far is aiming towards these type of questions, okay? Bringing everything together. Differentiation, implicit differentiation, turning points, quadratic simultaneous equations. Everything is built into this point. Brilliant. Okay. So, we're going to have a look at this little part now, which is using the second derivative. So this is actually new to this year, not that that makes any difference to you. So the way that we always think about this, now I always like to, I think I did this in the, when we were in when we were in AS, and we talked about the second differential. Why is it the fact that when it's positive, a positive change, positive d2y by dx squared, it's actually a minimum point? And then we talked about this, didn't we? If I was to draw, let me draw my minimum here. So if I've got a minimum there like this, and I'm finding my second differential, it's going from here, so from a negative to 0 to a positive value. So it's going from a negative gradient to a 0 gradient to a positive gradient. So notice that this is going like this, isn't it? So a minimum is when we've got a d2y by dx squared being greater than 0. And it works the same for the opposite. So for if I've got a maximum like this, and I'm thinking about this one here, why do I need a negative d2y by dx squared? Well, if I think about here's my gradients of all of these. So here I've got, I'm going from a positive value to a 0 to a negative value, which looks like this. So if I've got a maximum, we know that d2y by dx squared is going from a positive to a 0 to negative, so it's going to be less than 0 because it's changing. From positive to negative 0, it's going down, isn't it? Now, I'm going to talk about what these are now. So, when we're talking about a minimum, we're talking about a convex. So this would be greater than or equal to, and should be less than or equal to. But when we are talking about a minimum, we're talking about a convex. So if we look over here, in this one here, this is called a convex. F of x is convex when f double dash of x squared is greater than or equal to 0. Now the reason this is greater than 0 is, remember, we've got that minimum there. So like here, the reason this is a minimum is because we're going from a negative value to 0 to a positive value. So we've got this upwards trend, which means I need to be greater than or equal to 0. And when it's kind of got this is what's called a convex, like this. So we've got a convex, swerving left. We've got a concave. Now this is when we've got our maximum. If you see here, we've got this here. We're going from a positive gradient to a 0 to a negative gradient. Positive to 0 to negative, which shows I'm going down, which shows that my second differential here is going to be less than 0. Like so. And my point of inflection is when we are equal to 0. Now they're going to ask you things like this. So show the range of values when f of x is concave. Show the range of value when f of x is convex. Show the point, find a point of inflection. Okay, they're going to ask you these particular questions. And it's definitely worth getting these 3 down because you're going to need to remember them. Here like so, here like so, and here like so. So let's start having a look at some of these questions then. Find the interval on which the function is concave. Is there a way to remember this? No. So we know that when we've got a concave curve, we know that f, which we don't have to, it doesn't have to be f double dash. It is, this one's here f of x, so we'll do f double dash. We know that f double dash of x is less than or equal to 0 when we've got a concave. So let's first of all find out what f double dash is. So f dash of x is going to be equal to 3x squared plus 4, just like so. I'm differentiating f of x. F double dash of x is equal to 6x. So now we're going to say that concave when f double dash of x is less than or equal to 0. So we're going to say that 6x is less than or equal to 0. So x is less than or equal to 0. Let's just check that. Yeah, perfect. So there's our first one, nice and easy. So this next one here says, show that f of x is convex for all real values of x. So this one here is a little bit trickier. So first of all, we know that convex is when f double dash. Let's write it down. So convex when f double dash of x is greater than or equal to 0. So that's what we're trying to show. We're trying to prove that f double dash of x is greater than or equal to 0. So let's do that. So let's first differentiate this. So we end up with f dash of x. Well, if I differentiate e to the x, that's going to be e to the x. But don't forget there's a 2 inside there, so that's going to be 2e to the 2x. And if I differentiate this part here, that's going to be equal to 2x plus 2x. Then f double dash of x is equal to, I need to differentiate this again. Again, e to the 2x is going to be e to the 2x, but then I've got to differentiate inside that and times by it. So it's going to be 4e to the 2x. If I differentiate this, it's going to be plus 2. So if I think about what this graph actually looks like, well, 4e to the 2x means I'm going to be going, it's still going to be a curve like this, isn't it? But up by 2 means I've actually got an asymptote at 2. So let's draw that asymptote at 2. So this is going to be y is equal to 2. So then 4e to the 2x is, it looks like this. Now be careful, this isn't 1 because it's times by 4. So it's going to be, if it was times by 4, it would be 1 times 4, which is 4. But up by 2 is going to be, this is going to be equal to 6 here. So therefore, as f double dash of x is always greater than or equal to 0, f dash of x is convex for all real values. Like so. Brilliant. Let's just check that. Yeah. Therefore, as f double dash of x is greater than 0 for all values of x, it's convex for all real values, which makes sense. Last one then. So curve C has an equation y is equal to x cubed minus 2x squared minus 4x plus 5. Find the coordinates of the points of inflection. So, I mean, I think this is straightforward now. You can probably do this one yourself. So I will go through it just to get it, just to make sure we understand. So first of all, now, point of inflection is when, so d2y by dx squared, which is the second differential, is equal to 0 at point of inflection. Okay, so let's just differentiate this first. So dy by dx is equal to 3x squared minus 4x minus 4. So d2y by dx squared is equal to 6x minus 4. And we know that it's equal to 0 at this. So 0 is equal to 6x minus 4. Take the 4 over, divide by the 6. 4 is equal to 6x. Divide by the 6. So x is equal to 4 over 6, which is equal to 2 over 3. Just check that. 2 over 3. Ooh, wants the y coordinate as well. Silly me. So then let's sub that in for the y. 2 over 3 all cubed minus 2 times by 2 over 3 all squared minus 4 times by 2 over 3 plus 5, and that's equal to, I'm just going to steal it from down here, 47 over 20, 47 over 27. Brilliant. There's that then. I should have made you do that last one because there's no test your understanding on this one. Okay, so I think these are some of the trickier questions that come up when we're thinking about rates of change. You've got to really understand. I always find this difficult because I'm dyslexic, so I always find it difficult to read the question in this and make sure that I understand it, but you've really got to think about what the question is saying here, okay? So the next title, and this is actually the last little part of differentiation, is relating rates of change. So the rate of change of the area is A. The rate of change of the radius is 5. The area of a circle. So, sorry, it's talking here, it's talking through how we would think about this question to determine the rate of change of the area of a circle when the radius of the circle is equal to 3, given that the radius is changing at a rate of 5 centimeters squared. Now, there's lots of different parts here, which is we've got to think about. So, determine the rate of change of the area, okay, of a circle. I should probably highlight that as well. So, there's the first part. You've got to really get into the reading of this. When the radius is equal to 3, given that the radius is changing at a rate of 5 centimeters squared. The radius is changing at a rate of 5 centimeters squared. Now, the thing to kind of watch out for here, which I always find helps me, is to think about these units. The units will help you. The radius is changing at a rate of 5 centimeters squared. So the rate of change of the area, first of all, let's write down what that's equal to. So the rate of change of the area, this is equal to dA by dt. Now the rate of change means how is this changing in terms of time? Okay, not in terms of the radius. So how is this changing the rate of change of the area? And this is important actually. Whenever you see the word rate, think about dividing by dt. Okay, the rate of change of the area means divide by dt. So the rate of change of the radius is 5. With this one here, the rate of change of the radius, which is the radius over the rate of change, is equal to 5. So I'm going to say that this is equal to 5. And we also need to know the area of a circle. So the area of a circle is equal to pi r squared. Now, why do I need the area of a circle? It doesn't mention it up to the top, but it's because it says the rate of change of the area. Now, once we understand those parts and we've picked out what we want, take note, we're looking for the rate of change of the area. Now, the problem you've got is, if I want the rate of change of the area, let me just write down here, that's equal to, the rate of change of the area is equal to dA by dt. That's what the rate of change of the area is. Now, I've got a formula for area in terms of radius, but I haven't got a formula for the area in terms of t. So what we do is we use the chain rule. And what we say is that dA by dt is equal to dA by dr, which I can work out because I've already got a formula in terms of the radius. So dA by dr, okay, but I've got to keep this the same, so times by dr by dt. Now notice that if again I was to cancel these out, you'd end up with dA by dt. Okay, but I'm not going to cancel those out. I'm going to use them. So then all I need to do with this is once you've got all of that and you understand how to do it and you understand what all of these parts mean, you just substitute it into this part here. Okay, that's all we're substituting into. So my rate of change of the area, dA by dt, is equal to the rate of change of the area in terms of the radius. So first of all, I actually probably do need to work this out. So over here, I've got the area in terms of the radius, which is pi r squared. If I wanted dA by dr, this is going to be equal to 2 pi r. Bring the 2 down, differentiating with respect to the radius, times by the 2, 1 from the power. So then I can say this is equal to 2 pi r times by dr by dt, which I know is equal to 5. Rate of change of the radius. Just checking that's right. The rate of change of the radius. Yeah, good. So times by 5. So this is equal to 2. No. This is equal to 5 pi r. 10 pi r. Now it's asking for this when the radius is equal to 3. So when r is equal to 3, then I can say that dA by dt is equal to 10 pi times by 3, which is equal to 30 pi. Units on this, well, it's the rate of change in the area, so that's going to be centimeters squared per second. So that's a new type of question, that. And you've got to understand what all of these parts are asking you. Do you understand what the rate of change of the area is? Do you understand what the formula for area is? Do you understand that the radius is equal to 3? Do you understand that the radius is changing at a rate of 5 centimeters squared means dr by dt is equal to 5? Now all of this comes from this new word here, which is saying that the rate every time you see the rate, you need to think of d divided by dt. Okay, so we've got some questions here to have a little go at. So this is the question here. In the decay of radioactive particles, the rate at which the particles decay is proportional to the number of particles remaining. Write down a differential equation for the rate of particles, the rate of change of the number of particles. So in a now does it tell you any terms in this? The rate? I'm going to say, call it P maybe for particle. They've given it P. They've used N. Doesn't matter anyway. So, they've missed some parts out from what I've just seen, but we're going to make sure we understand it all. So, I'm going to start highlighting some of this. In the decay of a radioactive particle, the rate at which the particles decay is proportional to the number of particles remaining. The rate at which the particles decay is proportional to the number of particles remaining. Write down a differential equation for the rate of change in the number of particles. So this is what we're looking for. The rate of change of the number of particles. So let's just write down what some of these mean. So the rate of change of the number of particles. So this is going to be dN by dt. So the number of particles and the rate at which the particles are changing. Okay, is proportional to the number remaining. So the number remaining we're going to say is n. So let's call that n, which is the number remaining. Now the important part here, which is tricky and hard to spot, is the fact that it says decay. Now decay means that it's decreasing here. Just checking that. Okay, so it's the fact that it says decay means that these are decreasing. So what we're going to say is that the rate of change, the rate at which the particles are decaying is proportional to the number of particles remaining, which is n. Now, because I know the decaying, what we're saying here is that dN, now remember, you might remember this from GCSE, when we're saying proportional here, we're replacing this with a constant, okay? So this is dN by dt is equal to some constant k. Now, because we know that it's decaying, we're going to say that this is minus k n, okay? And that's done. That's all they're asking for at this stage. Write down a differential equation. Now, this is a differential equation, okay? Okay, it's an equation which has got a differential in it, okay? Write down a differential equation for the rate of change of the number of particles. Okay, so that's that part question done. Let's just check that. So let the rate of decay over time be this. Let k is often represented to use proportion. Let n be the number of particles, which is exactly what we did. So the rate of changing the particles, which we said here, is proportional to the number of particles remaining. Now, we've said that it's decreasing, so we've put a minus k. Now, if we were to work this out and work out it was a minus, then we don't need to worry too much about that. But with the fact that we know that it's minus, we've put in a minus in there. Okay? And that's because it's decaying. Okay. Let's have a look at another one of these. Newton's law of cooling states that the rate of loss of temperature, so straight away I'm thinking rate, so divided by dt, of loss of temperature, so T maybe, of a body is proportional to the excess temperature of the body compared to its surroundings. Write an equation that expresses this law. So, with this one, what we need to think about is the first thing that we need to think about is the fact that it says the rate of loss of temperature. So let's just highlight that. The rate of loss of temperature. We know that this is equal to the rate of temperature lost. Okay. Remember, it's the rate of loss of temperature of a body is proportional to the excess temperature of the body compared to its surroundings. So, with this one here, now I probably wouldn't actually use T. I probably wouldn't use T because it's the temperature, so I'd probably use theta of this. So I'm just going to change that. I'm going to call it d theta by dt. So the rate of loss of temperature and don't forget it's the loss, is proportional to the excess temperature of the body compared to its surroundings. So what we're thinking about here is it's the temperature of the body, so it's proportional to the temperature of the body compared to its surroundings. Compared to the surrounding bits, which is a bit trickier, because we don't know what that is. So we know that this is proportional to the temperature of itself minus the temperature of its surroundings. I'm going to call this theta 0. Now remember, proportional means k. Because it's the rate of loss, we know it's going to be minus k. So this is going to be equal to d theta by dt is equal to minus k of theta minus theta 0. Now I think that's a tricky one. I don't think the questions that we get asked are as tricky as that. I think they're a little bit simpler. Just going to check that now. So yeah, because it's a decrease, we're going to say minus k, and it's the, just checking here, this is the temperature of whatever we've got, and this is the temperature of the surroundings. There's a reason we're going to do a few of these. So the head of a snowman of radius r loses volume by evaporation at a rate to its surface area, a rate proportional to its surface area. Assuming that the head is spherical and that the volume of a sphere is given as V is equal to 4/3 pi r cubed, and the surface area is equal to A is equal to 4 pi r squared, write down the differential equation for the rate of change of radius of the snowman's head. So this is more like what we would get as an exam question. Okay, so we do still need to really have a think about what we're writing here. So the head of a snowman of radius r loses volume, so it loses volume by evaporation at a rate which is proportional to its surface area. So, head of a snowman of radius r loses volume, so it's going to be a negative, by evaporation at a rate which is proportional to its surface area. So, first of all, we talking here, what we're trying to find the rate of change of the snowman's head. So we know we're trying to find dr by dt, the rate of change of the snowman's head, of that r. Now what we don't know is anything in terms of the radius, so we need to work out what the radius is in terms of the volume, which we can do, times by the volume in terms of t. Now what I've done is I've split that up there. Now the reason for that is because have they given us here so why, give me a second. So the rate of change in the radius over the rate and change of v times by the rate and change of v, the rate and change of t. So the first thing I'd probably do with this is I'd probably find out what the rate of change in the volume is. Then I need to think about forming an equation for this, forming a differential equation. And then I need to substitute everything in. So what does it actually tell us? The radius of snowman's head loses volume. Radius of snowman's head loses volume at a rate which is proportional to its surface area. Loses volume. So what we're saying here is loses volume at a rate which is proportional. dV by dt is proportional to its surface area. It's proportional to the surface area, which we're going to call A. So then this gives us dV by dt is equal to minus Ka. Yeah, that's right. So that's our starting point here. It's just understanding this. This isn't easy, okay? You've got to really think about what it's saying. So dV by dt is proportional to the rate of its surface area. So write down the differential equation for the rate of change of the snowman's head. Now, this is the formula that we are dealing with here. Okay, we're trying to find this, dr by dt. We're trying to find dr by dt. Now we've got to find dr by dv first. Now we can't find dr by dv, but we can find dv by dr here. So dv by dr is equal to, well, first of all, I know what v is, don't I? I know that v is equal to 4/3 pi r, capital R, isn't it? R cubed. So dv by dr is going to be, well, that's going to actually, dv by dr is equal to 4 pi r squared, which is actually the surface area. We're not going to talk about that now. So we know what dv by dr is, but we don't want dv by dr, we want dr by dv. So dr, that should be capital R. dr by dv is equal to 1 over this, 1 over 4 pi r squared. Okay. So now I can sub pretty much everything into this. So dr by dt is equal to dr by dv, which we know is 1 over 4 pi r squared, times by dv by dt, which we know is equal to this minus Ka. But don't forget, we know what A is. A is equal to the surface area, which is the 4 pi r squared. So we end up with dr by dt is equal to 1 over 4 pi r squared times by minus K times by A, which is also actually 4 pi r squared. So I can cancel both of these. They cancel, don't they? It's going to be that one and that one cancel. So what I'm just left with actually is that dr by dt is equal to just minus K. And that is your differential equation. It is tricky, this. Very, very tricky. These questions do come up though. So what this is telling us is that this is decreasing at a constant rate proportional to minus K. So let's just check all of this. So I'll give you a second to get all of that down. Okay, let's very quickly go through this then. So just check those answers. So the first thing that we need to know is this part here was that dv by dt is equal to minus ka, which is what we wrote down here, wasn't it? dv by dt is proportional to a, which is equal to minus because it's decreasing, minus ka. The next part, we need to use the chain rule. Now we're trying to find the rate of change in terms of t, but we can't find that. But what we can find is the rate of change in the volume in terms of the radius, and then we can cancel out those. Well, we'll not cancel them out, but we can use them. So then the last little part is we sub in everything in. Yeah, this is good. Sub in everything in, we can end up with see that these two here will cancel, so we just end up with dr by dt is equal to minus k. Brilliant. Alright.